Fine. Okay, so we're basically done with the first third part of the course, which is on background and foundations. This is understanding what files are. From a theoretical perspective, it's just some sequence of ones and zeros that can be interpreted in some way. That's called an application that interprets them. They can also be stored physically on hardware for the purposes, well, yeah, basically that means this kind of hard drive. Okay, so like a spinning disk hard drive. This is the way that data is stored. And this holds files, and it holds files with magnets. That doesn't really matter so much, but it has a certain capacity. It can hold a certain amount of ones and zeros. It's a larger amount, which is why we use these types of spinning disk hard drives, but they're slow. They're very slow. So you want to minimize how often you have to get something from the hard drive. Every time your computer has to visit the hard drive, it's like waiting in a really long line. You know, this is like 1,000,000 times slower than getting something off of RAM. Okay, things on RAM are very fast. I mean, the difference in this is like literally 1,000,000 times. So it's slow to access things on disk, but it can hold a lot. So databases store heap files or just, raw data on the disk, along with an extra file called an index file. That index file can be small enough to where by itself it can be loaded completely into RAM. And then that way, whenever you're accessing the data structure, it's not only a data structure, but it's also in RAM. So that's very nice. It might also be the case that the index file is kind of broken up into pieces. This is the case in, for example, a B+ tree, where it could be the case that the leaves of the tree could be stored on disk, but the upper data structure could be stored in something that could fit into RAM. Or for a hash-based function or hash-based index, you could load the first set of buckets into RAM, but if you have lots and lots of them, then they're going to be stored in another file, and that file will be like a secondary file to the index. Okay, the point of having data structures is to organize data such that you can take advantage of some properties. We've talked about algorithms, search being the most important one. Okay. Good. So today I want to start getting into the theory of databases. And we'll start there. Before I do that and move on to sort of section 2, are there any questions about the first section of this course on background and foundations? No. Wow. Okay. Okay. Uh, fine. So, um, for the theory of databases, we're going to be starting off with something called ER diagrams. Um, this stands for entity relationship diagrams. Oh, oh no. Okay. So these are entity relationship diagrams. Okay, so at a high level, these are diagrams, so like they're kind of like pictures that are comprised of two major components. Those are entities that are like things that exist, and relationships, which is how entities are connected with each other. Um, but based on my previous experience, I think that there should be a few students who have already had some experience with ER diagrams, maybe students in BATE or something. Is there anybody who can, MIS, great. Um, yeah, Afreen, can you tell us what you know about ER diagrams? Like what's your background in them?
Yeah, I remember doing them, making them in MIS. I think what we did is we had a table and then the entity relationship diagram mapped out the relationships between the different attributes in the table.
Okay, and so,
Or
mhm.
uh, I'm trying to remember, or maybe it was there were multiple tables and it was mapping out the relationship between the different tables. That might have been it.
Okay. It's like, do you remember, like, did you draw them yourself or did you use them somehow?
Yeah, so I remember having word problems and then we would have to draw the diagram.
Mm. Okay, cool.
But
Thanks.
sorry, it's been a long time.
Yeah, great. Okay. Does anybody else remember anything about ER diagrams? Entity relationship diagrams?
Professor, I remember doing it in like SQL. So we had to create the relationships between the different tables. For example, there was like one to many or like many. I remember doing that. Yeah, that's what I remember.
Okay, great. Can you, what is this one to many thing? And do you remember any of the others?
Um, yeah, I know there was one to one and then many to many and then one to many. Um, I'm trying to remember the other ones.
Okay. And what was the point of this? Of the one
It
to
was
many, many to one? Yeah.
it was to create the queries, right? In SQL with the different tables that we had.
To create queries. Um, okay.
I'm not
Okay.
sure if I'm using the right like definition, but
Okay. Sure. Cool. Um, okay. Uh, anyone else? Yeah, so these are types of relationships. Um, okay. So I don't know. Okay, well, I'll give my take on ER diagrams. It's good that you guys have been exposed to them previously. Maybe you know everything I'm saying, or maybe I can put things in a different perspective. I don't know. Um, um, one thing that in this course we're going to be going back and forth, thinking about the same thing, but just from different perspectives. One way that we're doing that is by thinking of things as tables. So sometimes they're called tables, like a table, whatever. Sometimes it's called a table. Sometimes you oh a relation or an entity. It's kind of, yeah, it's kind of entity. So this is one way of thinking about things, from sort of like the table way. So you have a bunch of data, and that data has attributes. Okay, and you store it in rows and columns. And that's one way to think about all of the data that you have. And this table has a certain number of rows, it has a certain number of columns, etc. The other way is to think about these things as sets. So this could be sets in sort of the math sense, like the set 1, 2, 3, 4, 5, 6. The squiggly brackets there denoting a set of numbers, the set of numbers 1 through 6. So that could be the set that represents the faces of a die. You can also view sets as, in a kind of pictorial way, by making the set sort of inside of a bag, and everything inside of the bag is what's inside of that set. So I've drawn a circle, which is kind of a bag, and this bag is going to have points in it, or elements. So these are points, element, vectors. These are all the same things, but yeah, we'll get to this set perspective more when we talk about relational algebra. Relational algebra is for making queries. ER diagrams are not for making queries, it's for organizing your tables and enforcing constraints on the tables such that certain relationships are preserved. So the set idea we'll kind of come back to, but the sort of both of them are equally valid. It's like, is light a particle or is it a wave? It's both. Just whichever circumstance you prefer one interpretation, use that one. It's good to know both, though. In the set sort of perspective, one of these points corresponds to one row of the table. And a row of the table could be somebody's name, John, their age, 33, blah, blah, information about them. And so then this point would be a point, John, 33, blah, blah, blah. And this is a vector. Each of these points would have one dimension that corresponds to each of these columns and stuff like this. So the important thing, how much storage does one point take up? Like 1 millibyte. So first of all, there is no millibyte. A byte is 8 bits, and there's nothing smaller than a bit. There's megabytes. So it goes bit, byte, kilobyte, megabyte, gigabyte, terabyte, petabyte. I think the next one's exabyte. How much storage does one point take up? The exact same amount that row would take up in a table. So if this row in this table is very, very long, like it goes on and on and on and on and on, then representing that that row on a hard disk would take up a certain amount of space, and you could say that the point therefore takes up the exact same amount of space. These are the set perspective and the table perspective are both equally valid, and when so you can think about it either way. Sometimes problems are easier thinking about it one way. Sometimes problems are easier thinking about it another way. Now, we're going to be talking more about sets when we get to just before SQL. Basically, relational algebra is a way to write queries that's very, very much like SQL. Our SQL is actually sort of an implementation of it. Whatever. But for now, there's one property of the table that is a consequence of the fact that this table is also a set. That is that sets do not have repeats. Okay, so for example, this set that I wrote here, 1, 2, 3, 4, 5, 6. Sorry, let me make a better squiggly. Oh, that's terrible. That's a little better. Okay. If we had 1, 1, 2, 2, 3, 4, 5, 6. Okay, so we have one set of numbers, 1, 2, 3, 4, 5, 6. We have another set of numbers, 1, 1, 2, 2, 3, 4, 5, 6. For sets, there are no repeats. These are the same sets. They include the same things. It doesn't matter how many times one thing appears. So these are the same. And because repeats, taking any element and repeating it many times doesn't change anything, there's always the preference to just use the minimal set of elements. Okay, that's it. So it's a pretty simple idea. Okay, like we want to construct this thing called a set. It's a set is going to be like a bag, and the bag has things, and in this case, it would have 6 different things, like 6 balls with numbers on them, and I want to talk about those kinds of problems. So. Yeah, having things that repeat is not necessary. Okay. Now, because each of these points in the set, like this one, is made up of, it's just a vector that has one dimension John, and then the next 33 is its, it's like an X dimension and a Y dimension. I could say its X dimension is called John. It happens to not be a number. The Y dimension is a number. The Z dimension is who knows what. And in just that same way, this point is in like high dimensional space. It's not a hard concept. I mean, it's fancy sounding words, but this is all that it is. Let me pick on a student. I don't know if I'm just okay. How about Muskan? Muskan.
Hi, Professor.
Hey, how are you? Are you following what I'm trying to say so far with about sets and repeats and what a point in this set means?
Yeah, you prefer the minimal amount of elements because they're both like the same.
Right. So these ones that I highlighted in purple, that's an example of one set having and another set sort of repeating elements from it. So my question for you is here I've defined a different kind of point. Um, so what would a repeat of that point look like inside of this set? So in the same way that starting here, I was able to make a set with repeated elements. How would I do that with this one?
Maybe if the name John was mentioned again in another point.
If John was mentioned again in another point, yeah, okay, fine, okay, yeah, that works. Well, it can work. Okay, great, thank you. So one way that you could have, and that's true, if you happen to know that the x dimension here is a unique identifier, and that's the whole point why I'm talking about this, is that tables have a unique identifier, and they must have one. And that's not by accident. It's because that's the way that you have it behave like a set, because it is a set. I mean, it's not just any table. It's a relation. It's a type of set, whatever. So, one easy way to see that this is just copy the exact same point, right? So here I'll make another one that's John 33 and everything else, right? Let's say that I added another point to this set that was just a carbon copy of this. Okay, then I'd have one point appearing 2 times in the set, which is a waste. And the way that that would look like in the table, let me pick on another student. How about Rumit?
Hey, Professor.
Hey. Are you following what I'm saying about 2 points being the same in the set?
I think so, yeah.
Okay. And I'm trying to convince everyone that the set sort of view and the table view should be equivalent. So how would 2 points that are identical appear in a table from the table view?
I think 2 points that are identical in a set, if we wanted to replicate that in a table, but we wanted to keep like those set characteristics of no repeats, I think.
But here there is a repeat. This is an example of a repeat. So what would a repeat look like in the table?
Well, I mean, I think then the record could just be repeated in the table, but I'm not too sure if that really makes sense in terms of the table.
It doesn't, but yes, that's an example of a repeat. If this were a carbon copy, if these rows were carbon copies, okay, so these are the same things. You don't have repeats in sets, and therefore in tables we have this idea that there can be no repeats. Something cannot be repeated in the table. In particular, that means that there's no one row that is exactly identical. In addition to that, you could have a bigger constraint or a more severe constraint on what you're allowing to be repeated. So the previous student said that, for example, if you had 2 Johns, then that would count as a repeat. That could be. So that's a rule to say that things cannot repeat according to this. At the very least, that means that no 2 rows will repeat. But with a stricter condition, then you can, that's called a constraint. Constraint on X means no names can appear twice. This is the thing that would, in SQL, sometimes be called the primary key, or a key, okay? I.e. a key. So here, if X is the key, then it means that the name John can't be repeated. So let me get rid of some of these. Carbon copy, carbon copy. Okay, but this, 'want to avoid. Okay, so we want to avoid having carbon copies. So a loose constraint would be saying that for this entire table, nothing can repeat. That means that so long on any column that I change, then these entries can coexist. If I'm keying on the whole table. And then I can just make this entire thing the key. You know, every single thing glued together exactly like that. Nothing can appear exactly like anything else. But if I wanted to be stricter, then I could say that, for example, if X is a key, that then for this column, there can be no repeats, which means that before, when I was using this whole thing as the key, these 2 entries could happily coexist. But when I key by just this attribute, now these conflict with each other. Okay, so that's called a keyed constraint. You choose an attribute or a set of or a collection of attributes and say that with respect to those attributes, there can be no repeats, which means that they have to be unique. Okay. So yeah, okay. So an entity is going to be like a table. Okay, so this is an entity. Sure. Um, Trying to think of a pithy way of writing this. Okay. So here, that means that it could be one attribute. It could also be many attributes, okay? One is okay. You could also have many, and that's also okay. So the attribute or attributes, that define Sorry, I'm trying not to reuse certain words and stuff. Something like this. The attributes that define the requirement of uniqueness. That's, I could maybe write it better, but let's see. Okay, that's a better way of phrasing it. The attributes that define that which makes entities unique. So the keyed constraint is saying that these are the attributes such that no two entities with the exact same values for these attributes can be there at the same time. For example, okay, so these are the entries. Name is one column, age is one column. We have 3 points or 3 entries. I'll go back and forth with the language that I use. But these are 3 points. And now if we make a keyed attribute on both of these, then that means that the combination of name and age must be different. So here, John and John, these are okay because they disagree on their age. So long they're not exactly identical, then they're fine. The same thing here with these ages that are the same. Because the names are different, these are okay. This is when you have a keyed constraint that's using both of these columns. If I made the name by itself the constraint, the keyed constraint, now this is a stricter constraint, meaning that there's more of a chance for things to be kicked out. In particular here, the name John and John, because I'm only keyed on the name, these cannot exist together. So one of these would have to go. Amy would be fine. Now, similarly, if I keyed on the age attribute, well, now I'm saying that no two entries can have the same age. So here, either this John 33 or that Amy 33 would have to go. Like they can't both be there. Okay, so that's a keyed constraint. The attributes in which reference to things are unique. So here, if the keyed attribute is age, then all of the entries are unique by age. If it's name, then they're unique by name. If it's name and age, then they're unique. You can have many people with the same name so long they're not the same age. You can have many people the same age so long they have different names. Okay. Okay. Vocabulary. We have an entity. So because these are diagrams, we have to use pictures. And so, or, like I don't know what the constituents of a diagram are called. But we have an entity, and so that is a rectangle. We have a relationship, that's a diamond. Then we have what are called participation constraints. Participation constraints. There's 4, and we do these with lines. One is a thin line, one is a thick line, one is a thin line with an arrow, and one is a thick line with an arrow. Okay, so these participation constraints, all 4 of them are. The thin line is unconstrained participation. This is at at least one. At most 1. And this is exactly 1. Okay. Let's see. Now, these participation constraints are a little different than these relationship types, many to one, one to many, one to one, many to many. But they're kind of built into here. It's a part of these constraints. And that's it. There's like a weak entity. We'll get to that. Oh, sorry, I forgot. Attributes. Okay, so here's sort of the vocabulary. And just to put something into context, this is a typical example of an ER diagram. Okay, so this is some entity, E1. This is some entity, E2. E1 has two attributes, A and B, and A is the key for this attribute. Similarly, E2. So one way to partly see this is this E1 is like a table, E1, that has A and B as the columns, where A is the primary key or the key, the keyed attribute. Now here, for ER diagrams, the data particulars don't matter at all. The only things that the ER diagram is looking at is are the names of the attributes. As far as like what the particulars are of that's actually filled up, ER diagrams aren't involved with that. The only thing that they care about is, or the only thing that they're designed for is for talking about what are the columns that you have, like what are their names and types, and which one's the key, or which ones are the keys. And so similarly here, E2 would be a table with a column C and a column D, and D would be the keyed one. Yeah, so this ER diagram, just think about that part of the table, the name of the table and the columns of the table. Similarly for EC2 or E2, this represents the name of the table, and then this thing together is the name of the table and the name of the columns. The relationship can also be represented with a table, and we'll get back to that. But the point is that here, if we have some table with some data, and here we have some table with some other data, is there any way in which these two things are related? Where let's see. I'll add another one here, A. Okay, so imagine A is like name. I don't know, John. And now here is John also appears. And this is his age. And this is his address and I don't know, car type. Okay, so here's these two different tables that both have information about John. What if I wanted to combine the information about John from both of them? That's the role of this relationship, is that somehow we know that this contains something about John, this also contains something about John. How can we like relate them together? And so that happens through a relationship, and so you could, for example, relate A and D, where because this is unique for this table and this is unique for that table, you can create kind of a temporary middle table that can combine their information, whatever. I think it's helpful to remember that these ER diagrams are actually tables, especially later when you see an ER diagram and then you try to draw the table or what. I'll keep those. Okay. So, participation constraints. Okay. Let's say these are books, and these are people. So these are going to be our entities, okay? We're going to have some entity books, another entity people. And let's say we have the book Three Body. We have the book Alice in Wonderland. People. John, Amy, Paul. Okay. So, we want to have a relationship between people and books. So here there's going to be a relationship. Okay. We could have, let me pick on a student. How about Yonghun? Hey, how are you?
Hello.
Hello.
Good. How are you?
Okay. So, what I'm going to do is I'm going to draw sort of a thing here with. Okay. So let's say that some of these people like reading some of these books. Can you just tell me which people like to read what? You have 3 people and 4 books. You can pair them however you like.
So I can choose?
Yeah. It's your big day. You get to choose. What does John like?
Probably Three Body, Journey to the West.
Okay. Three Body. Journey to the West. Okay.
And Amy likes Alice in Wonderland.
Okay.
And Paul likes Winnie the Pooh.
Paul likes Winnie the Pooh. Okay, very good. So this is which books people like to read. Okay, good. Now I'm going to ask you a similar but different question. which is the which books do different people own? So John likes to read Three Body and Journey to the West. Which books does he own? Does he own both of them? Does he own other books? Does he own none of them?
He owns none of them. None of them.
Okay, he owns none of them. All right. And how about Amy?
Amy has Three Body and Alice in Wonderland. Is it possible?
Sure. And Alice in Wonderland. Oh, sorry, I'm going to go this. I'm going to make these go the other way. So none of these books go to John. And Amy, you said Alice in Wonderland and what?
Three books. Three Body. I mean.
Three Body. All right.
Yep.
Oh, she's got good taste. Okay. And Paul?
And Paul has Winnie the Pooh only.
Only Winnie the Pooh. Okay, so that goes to Paul, and that's Amy. Okay, very good. Thank you. So I'm going to clean this up a little bit, and here I'm just going to remove these. So here, this is John and Amy and Paul. Well, whatever. No, I'll keep it there. I'll keep it. Let's see. Okay, so the point here is that for two entities, it's not a one-way relationship. The relationship always goes both ways. So for let's see. The relationship likes to read. We can see here that with one input, there are two outputs. So John likes to read more than one book. That means that going that direction, this is a one-to-many relationship. Okay, it doesn't have to be, but at least it is if the data is like this. For the others, this is a unconstrained. This is unconstrained. Unconstrained because you can have a point with no input. You could have a point with no input. You could have a point with one input in, one input out. Here's another one input in, one input out. But because we're allowing points to not have any connections, then this can be unconstrained. Okay. So I'll do this. Here is going to be an entity, books. Here, likes to read is going to be the relationship, and this is people. Okay, so books, I didn't write it, but they have a title, and that's going to be the thing that I'm going to key on. People, they have a name, and so that's going to be the thing that I key on. Whatever, I mean here, title. Right, then there's the title, and then here, the name. So I can put each of these in their own table. And if I write a constraint like this using two thin lines, then what I mean is that anything can happen insofar as people can read no books, they can read one book, they can read many books. And any one book can be liked by anybody. Any book can be liked by none or liked by exactly one. It doesn't matter. I mean, that's what unconstrained means here. So the point of this diagram is to try to figure out how to, what tables should we have, how many tables should we have, and what should they look like. So we want to capture this type of thing, where there's people who like to read some books and books that are like to be read by different people. And we want to construct a table such that there's a connection that's made. And it's that table that's going to represent their relationship with each other. Okay. Okay, so this means books can be liked by 0, 1, or many people. Okay, that's going in that direction. Books, they can be read, and then the participation constraint is 0, 1, or many. It's called a participation constraint because if you imagine that there's a particular book here, is this book connected to a person or not? If there's like a connection between them, then this point can be said to be participating in the connection. If there's no connection anywhere for this point, then it's not participating. Sometimes that can be okay, sometimes not. In this case, when it's unconstrained, that's okay. So there can be books here that aren't liked by any people. We can have some books that are liked by one person. We could have other books that are liked by many people. Okay, so this point represents the liked by 0. This point represents the liked by 1. And this last point is many. In this case, because it's unconstrained, all of those can exist. If I make this a little different, oh, sorry, I should write something else here because this is unconstrained. And also, people can like to read 0, 1, or many books. Okay. So for an entity relationship diagram, you'll have two entities. Entities can never connect directly to each other. Okay? Entities can only connect through a relationship. An entity can have many relationships, but it must connect to other entities through a relationship. A relationship has two parts. It has two constraints. One going to the one entity, another going to the other. So for every entity relationship section, there's two directions you always have to think about. One is left to right, and that is the way that books relates to people, is this left one, which is here. But also there's this, the way that people relate to books, and that's here. So there's always like two parts of the description. So now I'm going to take one of these and change it a little bit. And I'll invite anybody who has taken or who has done ER diagrams before to volunteer themselves, just to say what changed. So is that many to many? Yes, each of them are many to many. Okay. Anybody want to, let me move this down a little bit. Anybody want to volunteer themselves to just say how this is different? It's the exact same as above, except now I've put a thick line here instead of a thin line.
So now books have to be liked by at least one person?
Yes. So now books must be liked by at least one person. Okay. Do you agree with that? I guess. Okay. Yes, exactly. So here, now this is no longer unconstrained. This point here would not be allowed inside of this table. Okay, so that is a one type of participation constraint. We're now saying there's constraints to which points can participate. Okay, let me try. Another one. Any other student want to offer themselves to volunteer? It's going to be for that.
Sure, I'll go.
Okay, great. Just a minute. So I'm trying to be more complete, but I'm kind of messing things up as well. Okay, great. So I'll jump here now. Okay, fine. All right. Yeah, go ahead anytime.
So with the books, it's the same as the one before this. It has to be liked by at least one person, but each person can only like exactly one book. So it doesn't work because there's more books than people.
And people must like exactly one book. Welcome to the totalitarian regime. Okay. Books have to be liked by at least one person, and people must like exactly one book. You say that this can't work because there's more books than people.
Yeah.
What if there's exactly one book? Wait, I don't see the problem here. So let's see.
So like if each person can only like one book, but there's one less person than there are books, one book is not going to get liked by anybody. Because weren't there only 3 people and 4 books?
Right. So what that would mean is that, yeah, like one of those rows would have to get kicked out. I'm not saying that this is consistent with all of the each of these ER diagrams. It's not. You're right. One of these would have to go. One of these books wouldn't be allowed. One of them would have to be deleted. Otherwise, yeah, you. But there are other data that where it is true. So that data is the one that's okay. That data would pass these constraints. Okay. Right. So what he was saying was that there was 1, 2, 3 people and 1, 2, 3, 4 books. So books have to be liked by at least one person, but people must like exactly one book. So he was saying that even if these people liked the one book, there would be a book left over that isn't liked by anybody, and therefore this is sort of a contradiction, and things don't work. And he's correct that this would be the case, and therefore those 4 books and these 3 people couldn't exist under this under these constraints. Okay. Good. Okay. I hope that's enough examples. I think, I mean, you can, if you want to see more examples, let me know. But I think that, 3 is enough. And I mean, there's so many different combinations. I can't go through all of them. I mean, there's 16 of them. And I'm not doing all of them. Okay. So, let's see, ER diagrams have participation constraints. Tables have keyed constraints. the goal is to have the goal of using ER diagrams is to figure out which keyed constraints the table should have. Okay, so this is the point of ER diagrams. The point is that we want to create tables. There's going to be a lot of them, but tables can have keys, and these keys can make sort of more rules that restrict the data. And sometimes you want that, other times you don't want that. So which attributes should be the keys, and how can you make as few tables as possible? And be able to combine data from different tables together. Okay. I'm going to stick with this book's title. Likes. I would like to ask for a volunteer to help me translate this ER diagram into a table, into tables. Anybody remember how to do that? Even if you don't, you can guess. It's okay. So somebody comes to us with two lists. Here's a list of well, no more than that, I guess. He comes to us with some data. These are the titles of books. These are the names of people, and these people like to read these books. Books can be, some books aren't read by anybody. Some people don't read any books, and that's the way the data is. And now I want a database where I can search for books that are liked by people or people that like books. I want that like in a database because I hear that they're good for this gigantic amount of this particular data that I have. How do I organize it? I'll give you a hint for people. You need 3 tables.
So would you have one table for books, one for people, and then one that has title and name?
Okay. I'll just call it likes to read. And you say that this would have title and name. Okay, and I'm guessing that people then would have name and books would have name. Oh, sorry, title. So these are your 3 tables?
Yeah.
Okay, and now what are the keys? Every table needs key.
So for books, it would be title, for people, it would be name, and then for
Those are easy.
the middle one, would it be would be title and name?
Title and name, yeah. Right, so in this case, it's both. The reason why it's, can you explain why it's both and not just one or the other?
Because in that table, you'd want unique combinations of title and name, right? So you'd want it to refer to each, like you wouldn't want repeats in that table.
What kind of repeats?
Repeats of like the same name to one title, multiple
Right.
titles to one name.
Right. Okay, good. Yeah. But this is allowing one title to be read by many people. That's okay. Also, one person could read many titles, and that's also okay. So that's why you need both of these as a composite key. That's what this is called. Because books can be read by many people, and people can read many books. So this, people can read many books, you're enforcing by having well, anyway, they're both enforced here. Okay, so we have 2 minutes left. Great. So this is the way that it would look for an unconstrained relationship. Now, if I changed this and I said that well, I'll get back to that next lecture. So what we'll be going through is how do you take different combinations of these participation constraints and figure out what kinds of tables you should have such that those constraints are carried out. Okay, so that's it for today. Thanks, guys, and I'll see you next week.